This lecture involves one-sided limits like the last one, except I want to also introduce you to a new style of function. You may or may not have seen these before, but they're referred to as piecewise defined functions. It's a function whose values or the rules for it vary depending on what values of x you have. Here's the way they're typically written. I'm going to put 2x plus 3, but I only want that if x is less than or equal to 1. Now when x is greater than 1, I want to write it as x squared minus 2x. Now I'm going to let my calculator graph this for me. There is actually a way to make the calculator work with these things. Go into y1. Let me just for a moment, I don't actually want to put this in exactly yet. You know how you normally would graph 2x plus 3. I got an extra parenthesis. I need to take that out. Delete that. And then typical zoom 6. This should not surprise you. It's going to be a line, and it goes right through the heart of the graph. Now, I'm going to show you what happens when I change it so that it looks like the function I've written. I'm going to put parentheses around it. And then, just like I'm multiplying, I'm going to start a new parenthesis and put in the parentheses x less than or equal to 1. So I've got to go to second math, that's the test menu, and then I want number 6. Put a 1 and end the parenthesis. Now look what happens when I graph it. Zoom 6 like before. The graph stops when I get to x equal to 1, which is exactly what I wanted to do. Now I can put the other piece in there in y2, but this time I'm going to attach the x greater than 1 to it. So let me put in parentheses my x squared minus 2x end of the parenthesis, start a new parenthesis, and in there put x greater than 1. So back to the test menu, which is second math. I want option 3, and the parenthesis, and I'll just do zoom 6 again. That piece is a parabola. So you can see when x is less than or equal to 1, I get the line, and then when x is greater than 1, it does the parabola part. Let's go ahead and copy this, bring it in, and make some notes about what the graph that we're seeing. Let's stretch that. Now I want to make a note here. The graph part that is the line actually includes x equal to 1 in it. So at the end of it is not a hole, it's a solid dot, because x equal 1 is actually permitted. The bottom one, or the parabola part, has a hole to begin it because x is greater than 1 there, so it does not include 1. Now you can either use the graph, or you can there's hundreds of ways you can do limits. Now hopefully you've seen a few of them, and you can realize that there are so many ways to solve these things. Here, since I can see the limit's not going to exist, you can tell because it's broken. It's too broken to even have a limit. So what do we say? What's just the limit then of this function? Well, sorry, let me start with the limit as x goes to negative 1. X goes to 1 from the left. Sorry, I said that wrong. When x is less than 1, the rule is 2x plus 3. So I can just plug in the 1 plus 3. End up with 5. Now look at the right limit. X goes to 1 from the right. The rule for numbers bigger than 1 was x squared minus 2x. So that's what I'm going to use in this instance. And you could, like you could plug in the 1 and get -1, or you can actually read it from the graph. Oops, I didn't mean to write in blue down there. It's the y value associated with that hole is -1. So that's my answer for the right limit. So now you know, when the right and left limits aren't the same, the limit itself does not exist. These piecewise defined functions you'll find used, in fact you're going to see them as long as you stay in math from here on out. They're very useful to have different formulas for different values of x. Well, anyways, the whole gist of this is that the limit as x goes to 1 of f of x does not exist.